Quantum computers have been hailed as the future of computing. If the hype around them is to be believed, they could offer computing power many orders of magnitude in excess of what we have today. But is this really the future of computing? And how do these enigmatic machines work? In order to understand the potential of quantum computers, it is useful to briefly touch on how traditional computers process data. Information is processed in the microprocessor. The microprocessor essentially performs a series of either-or calculations based on strings of ones and zeros called bits. The microprocessor is packed with extremely tiny components that work together to keep track of the strings of ones and zeros. The more components, the faster and more powerful the computer. The components on microprocessors have been steadily reducing in size over time. However, there is a limit to the amount of components that can be fitted onto a microprocessor. Eventually, they will reach the limit of miniaturization when the components are no bigger than an atom. This is where a quantum computer comes in. At the quantum level, things work differently from how they work in the macroscopic world. Tiny particles, like electrons and photons, can simultaneously take on states that would normally be considered mutually exclusive, like on or off. They can, in essence, be in two or more states at once. This attribute of quantum particles is called superposition. For example, an electron has two possible quantum states, spin up and spin down. When an electron is in superposition, it exists in a complex combination of both up and down at the same time. However, when the electron's state is measured, it drops out of superposition and adopts one position or the other. This is the underlying principle behind the famous thought experiment Schrödinger's cat.
We might consider Schrödinger's cat,
where the cat is both dead and alive until the box it is in is opened. But this is not just an interesting mental exercise. It could also be put to work. This is because, in theory, the phenomenon of superposition frees us from the limitations of the binary calculations that computers rely so heavily on. With the right algorithm, it is possible to take advantage of superposition to perform calculations incredibly quickly. Rather than bits, information would be stored and processed by superposition particles called quantum bits or qubits. Many different quantum particles have been proposed for use as qubits. We could use a single photon, the nucleus of an atom, or even an electron. But by the way of example, let's use the latter. All electrons have magnetic fields and can be thought of as teeny tiny bar magnets. When placed in a larger magnetic field, they will align with that field, just like a regular navigational compass. When this occurs, the electron is in its lowest energy state, zero, if you will. But it is possible to put the electron into a one state by applying energy to it. With enough applied energy, we can cause the electron to align 180 degrees against the influencing magnetic field called spin up. So far, so good. And you would be forgiven for thinking that this is the same as the traditional dichotomy of 1 and 0 currently used in computers. So what's the big deal? Unlike their binary forebearers, qubits can exhibit 0, spin down, 1, spin up, or both simultaneously. With a certain probability of each scenario, you will only know with certainty which one exists once you observe the electron. Using algorithms, this uncertainty can be harnessed to process many times the information of traditional bits. But that's only part of the story. The true potential of quantum computers comes when you combine several quantum particles. As you scale up the number of qubits, n, the amount of information contained within a quantum computer, rises to 2 to the nth power of classical bits. Quantum computers can thus handle exponentially greater amounts of information than traditional computers. It is this characteristic of quantum computers that could, in theory, give them their superior computing power. But this is also a potential flaw. They will not be very useful for most ordinary computing functions, which need to use a classical algorithm. If you had a quantum computer at home today, it would likely take longer to stream a video or type out a document than on your trusty old PC. as less information is required to obtain a result from the PC. But for highly complex algorithms, like those involved in encryption, they could prove invaluable. It is for this reason that many experts believe quantum computers will never really supersede classical computers, at least for everyday functions. But the technology is still in its infancy. Only time will tell.